In this video, we want to look at these four examples of multiple graphs, or graph of a function f and its derivative f prime, both on the same set of axes. And we want to determine which one is the function and which one is the derivative. So what we can look at in previous examples of this, we looked at where functions were increasing and where they were decreasing. So for example, in 101, if we were to look at the parabola shape, you would notice that that parabola is decreasing all the way from negative infinity up to 0. Since the function, if this were the function, since the function is decreasing, then the derivative should be negative. And what we should have for the other function is all negative values up to 0. But we don't have that. The other graph is sometimes negative, more time positive. Well, it's mostly negative up to negative 3, and then it's going to be positive from negative 3 to 0. So that cannot be, the parabola cannot be the function in that case. So I'll erase those lines. Now we'll look at the other function. The other function is increasing up to somewhere between negative 2 and negative 1. And that means the other function should be positive up to that same x value. And we see that it is. At that point, the blue curve, or the cubic function there, has a horizontal tangent, and the other function has a 0 at that point. From there on, the blue curve is decreasing all the way from between negative 2 and negative 1 up to between 1 and 2, and during that period of time, the other function is is negative. So we can see when the original function is increasing, the derivative should be positive. Must be positive. So I'll write that down there. When f of x is decreasing, f prime of x must be negative. And when f of x has a horizontal tangent, f prime of x has to equal 0. And so we can see in problem 101 that the cubic function would be the f of x, and the parabola would be f prime of x. Now let's take a look at 102. Again, we'll use the same type of logic. If the hyperbola-shaped curve is the original function, then you can see to the left of x, all of the tangents are negative, which would mean that the other function would have to be negative for all of those cases, and it's not. So that tells me the hyperbola-shaped function cannot be the original function. Instead, if we look at the function that looks like two antlers, you notice that it's decreasing everywhere, and so its derivative should be negative. And at the very end, it has a vertical tangent, and so we expect its derivative to go to negative infinity in that case. So that is enough to clearly tell us that the function that looks like two eyeballs with antlers is the original function, and the hyperbola shaped is the derivative. Now we'll look at 103 and 104. Now again, we want to use the idea that when the function is increasing, the derivative is positive. When the function is decreasing, the derivative has to be negative. When the function has a horizontal tangent, the derivative has to be 0. And so there are a number of things that I can look at, but in 103, I look for a horizontal tangent in one function where the other function is not 0, which means that the tall oscillating graph cannot be the original function. If it were, then there should be a 0 in the derivative in the other function at that minimum point. So that tells me the tall oscillating graph has to be the derivative, and the short oscillating point has to be the function. You notice that the function is never negative, but the other one is. And since both have positive and negative slopes, that has to be the way it is. Now in problem 104, I'm going to use a different strategy. And I'm looking at the curve that passes through the origin. And to the left of the origin, there are negative slopes, but the other function is positive there. So the other function has to be the original function, and the graph passing through the origin is the derivative.